Hello, my name is Christopher Vinas.
I'm Dennis Moreno.
Juan Herrera.
Alexander Gill.
And we are Team 19. For our problem statement, we had a 6 horsepower transmission. It was 1120 RPMs on the input shaft and 70 RPMs on the output, giving a 16-to-1 speed reduction. A few constraints that we had were the shafts had to be aligned, and whatever rotation you had in the input direction, you had to have the opposite in the output direction. As far as size and weight, we had to design it to have the smallest possible volume, smallest possible weight. It had to be able to be in use in high precision applications, endure light shocks, operate at room temperature, and cost was specified as not a critical parameter. In doing our research, one of the applications that we found was a mortar mixer, which takes advantage of the high torque, low RPM of the speed reducer. When we did our literature survey, we found that speed reducers in general were readily available from Boston Gear, Granger, Bison Gearing. Those are some of the main names. However, to find a specific one was a little bit more difficult. Prices did go up depending if it was helical gearing or spur, and also inline shafts made them more expensive as well. In doing our research, we found one that was very similar to ours, and it was $2,364. Ours is estimated as $1,900, keeping us competitive. When we started going through designs, our first design was to make it a 2-stage reducer. Very simple, very light, very small, using helical gears, but we couldn't find the gears in the selection that would take the horsepower under the given RPMs. For the second one, we went ahead and tried again with a 2-stage reducer with spur gearing since they had a larger selection, but we still couldn't find the gears that would take the horsepower under the given RPMs. Then, for the third one, we said, okay, we're going to go ahead and go 4-stage. Unfortunately, we tried to do it with helical gears and limited selection from Boston. We couldn't do it in a 4-stage. At that point, it was impractical to go any further with the helical gears. So we stuck with 4-stage, went with spur, and Juan is going to talk to you a little bit about how that went.
Okay, so in our actual design ended up being a 4-stage reduction, and we did 4 stages of 2-to-1 ratios, and with the final stage having an idler gear. It was 9 total spur gears, one of them being the idler gear, 6 shaft, 13 bearings, and the advantages of this was that the spur gears were stronger than the helical gears. They had a wider face area as well, and we were able to find all these gears, as opposed to the helical ones that wouldn't meet the horsepower requirement or the torque requirement to be able to perform in the system. Using this equation, this setup that we did in Excel, we were able to find the minimum teeth number, which was 14.16. Using this, we were able to find our minimum number of teeth and our teeth for all the gears that we chose, which you can see here for each stage. Once we picked the gears and the pinions, then we found our sigma stress, contact stress, and sigma bending stresses. Using that, we found our factor of safety for bending and contact stresses. And examples of this will be shown in the next slide. This is the bending for the stage number 4, where most stresses are applied for the gear and the pinion, and this is the contact stresses for the same too. Where, as you can see, those are the ones that had the most stresses. Also, right here, we picked for our shaft design. We started out with 1045 steel, and we selected it as a trial, and we ran it through at 1.25 bore diameter. It was 1.25 diameter for the steel, which was the same as the bore diameter of our gears. So we just used that throughout the system. We used sigma prime A, sigma prime M to find our factors of safety. For yielding, we used it using von Mises. And in the next slide, we'll see the two shafts which were under the most stress, which was shaft number 4 and the idler shaft. And it was under 5,400 pounds of torque for the idler shaft. And this right here, we can see the reactions that are happening at the endpoints of these shafts. Finding these reactions, we were able to find the max moment and the max torque occurring at them, and using the tangential and radial forces that were going to act at the bearings. Here you can see the deflections occurring on the shaft for shaft number 4, and also the moment occurring for that shaft. And here's the deflection for the idler shaft and the moment for the idler shaft. Originally, like I said, we started with 1045 cold drawn steel, and it passed all the tests required throughout the system, so we stuck with that one, and it had a factor of safety over 1, and the deflections were minimal in both the Y and Z planes. And now we're gonna have Dennis talk about bearings.
After some comparison between the Timken and Boston gear bearings, we found that the Boston gears actually handle more load, and they actually gave us a total machine life of 10 million hours before the gearbox needed to be rebuilt. As you can see here, we actually use our combination equations of 11.3 and 11.7. This allowed us to calculate the bearings for each of the 13 bearings that we have. Here you can see the actual design without the enclosure. It's we have 9 gears, we have 6 shafts, and 13 bearings. The case is actually designed out of aluminum. It's a 6061. It allows for ease of manufacture. It's readily available anywhere. It allows it's very lightweight. Here you can see the exploded view of our gearbox. And it's actually, you can see here we'll have a layer technology where you can just build each stage individually until you have the whole entire gearbox assembled. While the gearbox is capable of being machined, it also has a uniform wall thickness of 3/8. This also allows casting of the gearbox. And then lastly, you can put the 10 stainless steel bolts that bolts everything together. Here you can see the actual design of the gearbox. It has an offset of a small gear. This allows for a tight, compact design. And last, we're going to have Alex to close out.
Like Chris said, the estimate of our product is going to be around $1,932, and the prices of this power transmission can vary according to the manufacturer and the amount that we purchase quantity. The labor cost is also minimized because there's only 2 parts that we actually have to do. We have to machine the shaft and the casing, and the overall projected price is about $2,100 with the cost of the machining, and it's still going to be competitive. The maintenance has a break-in period of 1,500 hours. The oil change has to be changed every 5,000 hours, and there's a rebuild period of 10 million hours, where you would have to replace the bearings, replace the gaskets, and replace the eco oil. Here's the list of the bill of materials, where we listed down all the materials we used. And in conclusion, we've learned how to design a power transmission system using gear specifications, shaft layouts, force analysis, material selection, and bearing selection.